So taking a look at number 6 from exam 4 from 2014. So in this one, you have a bunch of different pi bonds, and you're actually given the products here. But even if you weren't given the products, in this case, you should still be able to figure this out. So essentially, you should recognize, well, here's HBr, so that's going to be my electrophile, no matter what. The molecule have 2 pi bonds. I have pi bond between 2 and 3, and pi bond between 4 and 5. So either of those could be a nucleophile, and actually one of those is a better nucleophile than the other. Anybody have a guess which one's the best nucleophile? It's either between 4 or 5. So either this pi bond, 4 and 5, or 2 and 3.
4 and 5, 2 and 3.
It's actually 2 and 3.
Why?
Why? Why would it be between 2 and 3? Because you're going to form the most stable carbocation this way. Remember, alkenes reacting with HBr make carbocations. Alkenes reacting with HBr make carbocations. So where should I put a plus charge at?
Carbon 2.
On carbon 2. Now, why would that be really stable?
Lone pair resonance.
Yep, lone pair resonance. Right? So you're used to saying, oh my God, carbon 4 would be a tertiary carbocation, right? That would be the next best answer. But really, at the end of the day, carbon 2 with the lone pairs right next to it would be even better. Now the problem with this one, is there any resonance? So there's one resonance structure. I could use these lone pairs, right, and draw that resonance structure. But can I use this pi bond to stabilize this? No, I can't, because now it's interrupted, right? This is an sp3 hybridized carbon. So I can't do pi bond resonance with this. So let's say, what if I had done it a little differently? Let's take the same thing. Do the same numbering. 1, 2, 3, 4, 5.
If you don't number your carbons, and you get the question right, do you get 4 points?
Yes. But if you don't number your carbons and get it wrong, you don't get very much pity from me.
But if I did.
Because I mean, again, I don't know. I do it every time. It seems to be working for me. You should maybe, I don't, what do I know? Okay? So let's say you were still convinced that you didn't recognize, even if you didn't recognize this about that carbon. Say okay, this one would be the most substitute. Let's use that. And we want to put a plus charge where? On 4 or 5, do you think? 4. 4 would be more likely. One, 2, 3, 4, 5. And then you have Br minus. So you easily could get, right, this to attack here.
Mm-hmm.
But now this carbocation, can you do any resonance with this carbocation?
Yeah.
Actually, yes, you can. This pi bond is now right next to it. So you actually could do resonance. And then guess what intermediate you just make there? The same one you just put before. So you that the idea of this problem was you could get there from 2 ways too, anyways. So that's the other thing, right? When you make a carbocation, start thinking about resonance and drawing all those resonance structures out. And then the last part says give another possible product, and all that means is it doesn't matter what. Just use the pi bond to attack and give something else that could have happened, right? You could have put a plus charge here. You could have put a plus charge here. Not that it's likely. I didn't say give another possible, more likely product. I said give another possible product, right? So just put another possible product there. Okay. Because even this product, actually no, this is not the same. I take that back. This is wrong. That's not that. If I move that pi bond there, what happens? Where's the pi bond ended between? Which 2 carbons? 3 and 4. Where's the pi bond here between 4 and 5? So it actually is different. Touche. That's why you number your carbons.
So for intermediate B, we had to do the resonance of the intermediate and then have the BR attack. So we can use
Yep.
pi bond? Okay.
You did. Yep.
Okay.
You did. So for the product B, you would have to do this first to get to this, I believe. Yep. So, but another possible product would have been the product of this one then, right? That could be another possible one. That would have made sense. That worked too. So
And so that's how you get those 2 answers.
that's how you get those 2 answers.
So then for this, you can't do H plus Br minus attack at the same time?
No, never have done, never have I done that with alkenes.
Yeah. Okay.
That's with alkynes,
Yep.
right? Alkenes go through a carbocation with HBr. Alkynes do not. They do a trans addition. But they can do it all at once, or they can make that three-member ring with H+. There's two different ways to do that one.
Okay.
So this is number 10 from 2015, exam 4. It says, provide a detailed mechanism for the following reaction. So numbering our carbons, 1, 2. No, let's just worry about the alkyne here. I can put 3. So we have BH3. So where is the boron going to add to? So we have an alkyne. Is this reaction regio selective?
Yeah.
Yes. So what carbon does it add to?
1.
Carbon 1, the less substituted carbon of the alkyne or alkene, BH3. How does it add? Is there stereoselectivity?
Yeah.
It's syn addition. Good. So you'll need to draw the boron, right? It has that empty p orbital. You have to know something about this. So it asks for the mechanism here. So the mechanism when you can do the mechanism. Now in this case, you can do this first part of the mechanism. The pi bond attacks the empty p orbital, and at the same time, the H goes to the more substituted carbon. All right, and they're added in a syn fashion. I would have drawn an H in here. I think it's helpful to remember that. There's an H there on carbon 1. 1, 2, 3. And now there's a BH2 and an H. Make sure you draw good bond angles. All right. sp2 hybridized, bond angles are 120. Careful there, don't mess those up. Step 2 was just the OH minus. You don't need to know the mechanism for that. Remember, that's just a switcheroo. So don't need to know the mechanism for that. We do need to know, okay, now it's this. Right, the BH2 is replaced with an OH. And now from this point, what do? What kind of functional group is this called?
An enol.
It's an enol, and enols do what? Tautomerize. So we're going to do a tautomerization here.
Make a alpha.
So the pi bond attacks there. And those 2 electrons in that OH bond go there. And that gives you an aldehyde. Now, one thing to not get confused about, is this final product cis or trans, or anti or syn? No, right? Once you do the tautomerization, you need to show this tautomerization where the OH and the H were syn, right? So that way I understood that, I know that you understand that this initial addition was syn. But once you get to the aldehyde, right, then I can't, right? There's no way to tell if it's syn or trans at that point anymore. So there's no way to tell. But I knew the step back it had to be, right? The OH and this H had to be on the same side. Good. Okay, so this is number 9 from 2014, exam 4. Again, looking here, what I would do to start, I would draw in the H's on my alkyne, number those carbons, 1 and 2. Where are they at in the products? I would say they're probably here, 1 and 2. How do I know that? Because that's where all the stuff, bromines and chlorines and stuff's at. Did I add carbons?
Yes.
Yes, I did. Now, so I added how many carbons? 4.
Well,
I added 4 carbons, but I'm going to have to add 2 steps where I add carbons. Right, adding carbons. I would have 2 steps because it looks like these are not the same, so I'm going to have at least 2 steps adding carbons. Let's finish numbering like that. 3, 4, 5, 6. That's the last thing I do, right? Once I get to the alkyne part, I add carbons, but one step back here would be what, do you think? So it's not going to be involving the carbons. It's going to be involve one of the other 2 things. So what do I have on there? I have, usually I have an H and a chlorine, and they're both what to each other? Trans. And I have an H and a bromine that are cis, but do you guys know any way to add H and bromine cis?
no.
Do you know any way to add bromine and chlorine cis? No, you know a lot of ways of adding bromines and chlorines trans, though, I think. But you got to be careful. The reason I think one step back, I guess it really doesn't matter. Actually, it does matter which is the first step to do back. You can add bromines trans with both an alkyne and an alkene, right? Can you add H and Cl trans with an alkyne? With an alkyne? Yes, you can. Can you add HCl trans with an alkene? No, you can't.
Can you like repeat that?
Right? Yeah. So think about it. So think about this. If I gave you an alkene and had it react with HCl, what are you going to make? What do you make when you react HCl or HBr or H plus with an alkene? You make a. And if you make a carbocation, are you going to be able to get things anti for sure? No. Right? So it does matter what you do first here.
So you can't have antis with a carbocation.
Right. Well, if you have a carbocation, you're not going to make an anti. So one step, so bromines I can add anti with an alkene or an alkyne. H and Cl I can only add anti with an alkyne. So what's the last thing I want to add to make sure they're anti? Actually the BRs. All right, so I want to take, if I take one step back here, I'm going to erase, I don't know, I guess I'm not going to erase that. I'm just going to put this away for a little bit.
So how many points would we lose for that?
Yeah.
I don't know.
No, I'm serious.
I don't know. Depends how else you did everything else right. It was worth 8 points, probably 2 or 3.
That last step?
2 or 3 points for one step.
There's 4 steps. So if you do the math, 8 divided by 4 would be 2. And does that, okay, so we want to add the BRs last then, because we know that we can add BRs anti with an alkene. So we'd have the H and the Cl trans. That's a number of carbons, 1, 2, 3, 4, 5, 6. Now what does this come from? This is an alkene with an H and Cl that are trans to each other. This had to come from what? An alkyne between the carbon 1 and 2. There you go. And then you'd have 2 more carbon-carbon bond adding steps. Hopefully we've done those plenty of times.
Then it doesn't matter, right?
Doesn't matter which one you do first. It doesn't matter which one you do first there. No. So moving forward here, you'd have just HCl, and here you'd have Br2. Right, so yeah, this is a tough one, right? This is, you gotta know your reactions inside and out, right? Can you add HCl trans from an alkene? No, you can't. What can you, so be thinking about the same things we did with the alkyne reactions where you had to write what were the products. You should have done that exact same thing with all the alkene reactions. Is this reaction stereoselective? Is it regioselective? Right? HCl with an alkene is regioselective, but it's not stereoselective, right? Because you make a carbocation. And if you make a carbocation, all bets are off. So yeah, then the final bits. Oops. Five, 4, 6. Right, so remember you can use your whatever your favorite base is going forward. Na, NH2, and we need to add that piece. Right, notice how the bromine's attached to, right, carbon 4 is the one we want to attach to carbon 1. So that's the carbon that needs to be attached to bromine. It's carbon 4. Same sets of reagents going this way. 1, Na, NH2, 2. Get a little crowded. No, forget it. Now I'm all over the place. That's close. For that reagent, you'd need.
And those need to be numbered, 1, 2.
You don't need to number them, but
Oh. But you do need to number.
I do it. Then you need that CH3 piece to get that last
Right.
carbon added there, which you've done plenty of times. So one of the questions, what if this was a Cl? Then it wouldn't matter if we did Br2 or Cl2 first, because from an alkene, right, versus down here, when you react an alkene with HCl, you get a carbocation. But if you react an alkene with Cl2, you get chloronium ion, right? If you react the same alkene with Cl2, right, remember you get the 3-member ring with chlorine. We always get trans additions there. It's regioselective and stereoselective then. Good. So for this one, so it's number 2 on 2014, and it's asking you for each set of resonance structures, circle the form that's most stable and explain why. Okay. So for this one, you have anions. So the first rule you always want to look for is, of course, the octet rule. So does everybody have a full octet in both of these resonance forms? Yes, everyone has a full octet, so that's great. Then what's our second rule we look for? We look for electronegativity. When we say electronegativity, what do you mean by that?
Like who can hold the charge?
Who's the most happy with the negative charge, right? The word electronegativity is not an explanation, right? Writing electronegativity is not an explanation. I can't emphasize that enough. Just writing electronegativity, that's a word. That doesn't tell me that you realize, in this case, oxygen is more electronegative than carbon, right? Oxygen is more electronegative, so it's more stable, right? So you need to say that. Right, so in this case, right, which resonance form would I pick? I would pick this one, right? If I had to choose who had a negative charge, if everybody has a full octet, I'd rather have the more electronegative element. In this case, that'd be oxygen. All right, taking a look at B. So again, 2 resonance structures. Does everybody have a full octet? Yes, they do. Everybody has a full octet. All right, so now in this case, you have a plus charge. So what's the difference? You have a plus charge on sulfur or a plus charge on oxygen. Okay. Well, which one's going to be more happy or less happy with the plus charge? Sulfur would be cooler with a plus charge because, again, it's less electronegative, right, than oxygen. So it's all about electronegativity again. So it'll be more stable with the plus charge. All right, here you have 2 resonance structures again. First rule: do they have a full octet? No, they do not. Do they both not have full octets, or does one not have a full octet? They both don't have full octets. Okay, so that means we're dealing with carbocation in this case. What are the ways you know how to stabilize carbocations? Hyperconjugation, lone pairs, and pi bonds. Okay, do you see any lone pairs? No, so it can't be lone pairs. Are either of these able to be stabilized by pi bonds? Yes, they are. Yep. So the difference here is this one can be stabilized by pi bonds too, right? And this one could as well. So you could say 2 things here. You could say this could be stabilized by 2 pi bonds very easily, or even simpler than that, this is the more substituted carbon, right? So even just not just necessarily hyperconjugation, but just a more substituted. I mean, really, it could be stabilized by 2 pi bonds, I would say. So I would say this, because it's more substituted, and it can be stabilized by 2 pi bonds from both sides, it's a more stable carbocation. So that one would be more stable. I think I've written more hyperconjugation. Because you could get resonance stabilization from here or from here. Whereas here you can only get it from one side. All right, for this last one, do we have full octets?
No.
Nope. So they're both on full octets. So they're both carbocations again. So now we ask ourselves, what are the ways to stabilize carbocations? Hyperconjugation, pi bond resonance, or lone pair resonance. So one of these is going to be more stable than the other one. Which one is it? First or second? First one, why? Because it's next to lone pairs, right? Are the bromines lone pairs drawn in? No. Are they there? Yes. I could even ask you to, maybe that could be something I do again. Say draw on all the lone pairs, like sapling makes you do all the time. So that wouldn't be the most stable because it's closest to lone pairs, right? Which means it would be most stable because of that. All right, so this is number 10 from 2014. We're 10 from 2014. Number of carbons, 1, 2, 3. Ooh, got a little turned around here. So let's make sure we know what we're doing. Actually, doesn't matter. 1, 2, 3. Did we add any carbons? Yes, we added a carbon. How many carbons do we add? One carbon-carbon bond. This is being added two, but we've added one carbon through a carbon-carbon bond. So we're gonna add a C. And that's we'll call that number 4, I guess. So working backwards, what do you want to do here? So let's take a look at what we have. So it looks like we have two H's that are what to each other? Trans to each other. We have a Cl and a methanol, O-methoxy, trans to each other. We have these two carbons that are trans to each other.
So like on this sheet, both of the hydrogens have wedges?
Yeah.
They're the same.
So for this one, you have the two H's. You have two H's that are trans, and you have a chlorine and this O-methoxy are trans. I usually will not worry about the carbons, right? Don't worry about the carbons. I'm looking for the chlorines and what they're trans to, the H's, what's going on there. So H's that are trans. How many ways do you know how to make H's that are trans? One way. And where does it come from? An alkene or an alkyne?
Well,
How many ways do you know how to make hydrogens to make them trans?
oh, actually, Alkene.
You know how to make, how many ways do you know how to make hydrogens trans?
One.
Just one. And what's the starting material when you do that? An alkyne. One step back from this is going to be an alkene or an alkyne.
Alkene.
An alkene. So that means those hydrogens already were on there. That's not one step back. Everybody see that? It's very similar to that HCl question we worked on. So I would say, right, we have an alkene one step back, and I'm starting with the hydrogens on there. Now why? I'm doing that because I can't make hydrogens trans from an alkene, but I can make them trans from an alkyne. Right? I know how to make hydrogens from an alkene. I can add hydrogens, but which way do I add them when I add them to an alkene? I add them cis. Right? Okay. So what else was on here? So I'm taking off the chlorine and this O-methoxy. Number of my carbons, 4, 1, 2, 3. One step back from this alkene would be what? An alkyne, right? Usually the first step back is always an alkene, right? Then an alkyne. So we kind of get used to that pattern. One, 2, 3, 4. Once you get to the alkyne, now you need to do your adding carbon steps. And we hopefully only have one of those, right? Adding that bond. So let's go forward now. So step 1, I'm going to use this way to depronate the base. How many carbons do I need to add? 1. That'd be carbon 4. What reagents do I need to make a trans alkene? Which one's that one? The lithium or Na. I need minus 78 degrees C and NH3. Very good. Now if I want to add, that gives me the trans alkenes. Now if I want to add the Cl and that O-methyl, what do I need to use? Cl2. Cl2 and methanol as a solvent. So I need this, but I also need to have an H, right? There as well. And that would give me that product.
So you could do the Cl2 and the HO carbon, 2 different steps?
No, that has to be the same. Has to be all the same step.
It does?
It has to all be in the same step. Yep, it has to be all in the same step. Right? These two, because I'm gonna make a Cl2, a bridge Cl2,
Oh, okay.
and then I need this to attack, so they end up being trans to each other. So another question, or maybe another version, what if these H's were on the same side? What if they were both on the same side? In that case, you could have done either of these steps, adding the H's or adding this, either way, right? If you would have done, if you wanted to add H's syn, you could do that H2 palladium on carbon from an alkene, or you could have added H's syn from here with H2 and Lindlar's catalyst, right? Then there's different pathways to get there. Good. So this is B this is B, part B, number 3, 2014 test, exam 4. And the gist here is actually, this one is the more stable resonance structure, and it has to do with aromaticity. So if you can make something aromatic, that's usually the best, most important thing you can do. It trumps all the rules, even the octet rule. Right? We're basically saying here is an uninterrupted pi system of p orbitals. Right? So this carbon's choosing to be sp2 hybridized, put these lone pairs in a p orbital. So that have 1, 2, 3 pairs of p orbital electrons in an uninterrupted pi system that make that aromatic. So even though this is a carbocation there, that's okay. It's going to react and be aromatic. It's going to be like that. Remember again, what do resonance structures tell us? They tell us something about how these things react. So where do you think nucleophiles would go on this structure? Where would nucleophiles attack? Carbon with plus charge, yeah. So this helps us understand how these things react, right? This actually helps us. No, it's not a trick question. This is actually a really electrophilic. So recognizing this helps us understand how this reacts, right? You look at this and you think, well, this isn't a very I see pi bonds, right? And you normally think nucleophile, right? Actually, in this case, this is an electrophile. Because this carbon's so delta plus because it wants to take these electrons and put them there that it's going to react with things. So this actually helps us understand, right? Again, why do we do resonance structures? What's the point? Is to help understand how things react.
So where that minus sign is, there's 2 lone pairs.
Yes. Right? So if I do the resonance form of this, it would be
I feel like that throws me off.
taking that right there. A minus sign
dots.
should be 2 lone pairs. You can draw them in.
Okay.
Yep. I might not, but they're there. Right? That's like taking those 2 electrons in that pi bond, and they both go to this carbon, and this has a plus charge. That's how you actually draw those arrows. You should be able to draw all these arrows too. So this is moving 2 electrons from this pi bond, which is like 1 lone pair. All right, so this is number 4 from 2014, number A, or letter A. Is this aromatic, anti-aromatic, or non-aromatic? And so the trick, or the thing you got to remember here, is something about boron. Where is boron at in the periodic table? It's in the 3rd row, or 3rd column, 3rd period, which means it wants 3 bonds, but that means it's 2 bonds, 2 electrons short of an octet, 1 bond short of an octet. So it's electron deficient. So it actually is sp2 hybridized. All borons are sp2 hybridized if they have 3 bonds only. So that would make this an sp2 hybridized boron. There'd be a p orbital there. So that would make this an uninterrupted p orbital system. And then you say, so if it's uninterrupted, awesome. Now how many lone pairs of p orbital electron, or how many pairs of p orbital electrons are there? And there are 1, 2, 3. So that's an odd number. So this is actually aromatic.
It's not anti?
It's not. Uninterrupted pi system and an odd number of pairs. Because boron's sp2. Boron doesn't have a lone pair, right? It's not like nitrogen. If it was nitrogen, there'd be a lone pair here. And then it could be anti-aromatic or non-aromatic. Right? It would choose maybe not. It would try to be not, yes.